We'll start with our RAI Digital Twin walkthrough. The main idea of this walkthrough is really to, let's say, to give the audience a grasp of how to operate the digital twin, and also to get to know the concepts and components as well as the input-output. And this is the summary of this presentation. We'll start out by laying out the concepts of the digital twin, what it wants to achieve, and what is composed of it. We are going to go through the environment preparation. So, I mean, the specifics of, let's say, what you need to in order to run the digital twin and so on. On the third section, we are going to go on the input and output. And when we talk about the input output, it's really about, let's say, what are the places that you can, for example, configure the parameters of the digital twin, or how you could modify, for example, how the output is generated. And the output of the digital twin, as we are going to see, consists of both data and reports. So we are going to go through that. We're also going to take a step about a section for unit testing, which is a great way to onboarding, because unit testing, let's say, the idea of things is really to test the fundamentals of the inner mechanisms. So in order to get ownership of the code, look at the unit test could be a great way of, let's say, make sure that you understand that everything is running as expected. On the fifth section, which is about the extrapolation cycle, we are going to go through all the parts of digital twin in regards to, let's say, download and retrieving the data, backtesting, doing system identification, and generate data that is associated with the future. The sixth section, which is primitives, is really about, let's say, getting understanding about the objects and classes and types that are being used on the digital twin, because this will make a lot easier to understand the model logic itself. By the way, this is the 70th section, which is really about, let's say, diving deep into the model inner workings, about the pieces that makes the high controller, or the pieces that makes the behavioral models that we use for future state extrapolation. And we'll end with questions and answers. So a brief overview of what is the RAI Digital Twin. The summary of it is that essentially it's an operational software in the sense that it must be maintained regularly. And also it has this goal of, let's say, being something that helps with the day-to-day operation or week-to-week operation. Another thing about the digital twin is that it consists of several functions around the cadCAD model. So cadCAD model, let's say, takes the role of being your representation of how the RAI system works. But at the same time, the digital twin does have several integrations that makes it suitable for operational purposes. They do that by accomplishing those 5 functions that you are seeing here on the screen. First one is about data ingestion, which is really about, let's say, collecting data from the graph sources, from the ETL data source from BigQuery. So every time that you run the digital twin, you are also downloading all the historical data that is available. It accomplishes also by doing historical backtesting. This consists essentially of, let's say, getting your cadCAD model representation of the system, get the historical data, and seeing what happens if we run the model on the past, and if we compare against the past data. The idea of that is really to, let's say, to know how successful is the cadCAD model in explaining the past. This is a critical step for any digital twin, for any model that, let's say, tries to do future state extrapolation, because this allows us to have a benchmark of how reliable and trustable is the model. Third step is about system identification, because on the cadCAD model, we have several components. We have, for example, the components which are more deterministic, which relate more to the smart contract itself. But we do have several components that are behavioral in nature. Like, for example, what are the actions that the users are going to take? If you have a price movement, are the users, for example, going to react adding or removing liquidity on Uniswap, or maybe buying more debt? There is no deterministic mechanism for that. So we need to use several behavioral models. And one key feature of the digital twin is that allows to experiment easily with those behavioral models, and also to visualize them easily. And a fifth function, which is also very important, is about report generation. Because the cadCAD model code it's I mean, it's all code that is not easy to parse for example, for a lay person. Also, the data ingestion, the data that is generated on the future state extrapolation, the historical backtesting, they are mostly CSV files. So in order to have, let's say, a good operation, in order to make results more shareable and to make interpretation easier, it's important to put emphasis on report generation, on making templates of reports that, let's say, every time that you run, you can get instant insights. This is a diagram that, let's say, illustrates how the software architecture of the digital twin works. As you can see, there are several blocks in there. But in an ideal world, what would happen is that here at the upper left, you have, for example, a routine. You could have a cron job, something that executes weekly, daily, hourly. It's really at the criteria of the user. And as you are going to see, it's not exactly difficult to, let's say, implement that at any regularity that we wish. We started execution. When we execute, the first thing that the digital twin must do is to prepare. So this involves retrieving the current data, which is essentially collecting events on Uniswap, collecting metrics associated with the RAI controller, and also getting the historical series of the prices. Once we do that, a natural step is to generate results about that, because there is this block here called visualization, diagnostics, and reports, which is really about reporting, because each step on the digital twin accomplishes a different task. So in preparation, we are interested in simply getting the data. When we go to backtesting, what we do is to use the past data and use that as an input to the deterministic mechanism of the digital twin. And the idea here is that we run the model in the past and we compare them against the actual data on the past. So we are essentially testing the deterministic mechanism. We want to see if our cadCAD implementation of the controller is getting the same results as the data that we are collecting about the controller behavior. Once we run the model, we compute validation metrics. Validation metrics, they are essentially loss functions. So you could get, for example, a loss, for example, on the redemption price on each point of time, another loss on the redemption rate, or maybe the total debt amount. It's a modular thing. You can have 1, 2, 5 validation metrics. There are some really way also on how you define loss functions. So you could talk about absolute error or squared error. By default, we are using squared error. There are places where you could modify that so that it suits better the validation metric. But it's important to note that, let's say, the definition of the validation metric itself, is a thing that is operationalized. As the model gets more complex, or for example, you need more, let's say, insight into the model reliability, this is a place that, let's say, it's possible to iterate. And of course, we generate a report about that, about the backtesting. After the backtesting step is done, and we are able to trust the model, we are interested into extrapolating into the future. We want to know what happens to the system over the next week. So the first step is to perform system identification, which is essentially fitting the user action models. Because, for example, one key variable of the RAI model is the Ethereum versus USD price. And there is no, let's say, obvious way of how you estimate that price on the future. So what we do, we have a stochastic process for that. That stochastic process makes use of some distributional properties. And we fit that stochastic process before. And I'm going to show afterwards where this is done. And we use that for generating several scenarios of future price scenarios so that we can use on the extrapolation. Another step 2 on the system identification part is about model parameter estimation. Because, as I said, we do use some behavioral models, like, for example, supposing what's going to be the typical user behavior over the future based on the past. So fitting those models, estimating those parameters is a thing that happens before the extrapolation. After we have those parameters, it's really about going on the extrapolation and using those parameters for, let's say, extrapolating future signals about the price and generating several scenarios for the future. Those scenarios for the future, they could involve a multitude of parameters. They could also, for example, involve of what happens if you change the mechanism. There is really, let's say, a diversity of things that you could do on the digital twin workflow. And after this is done, we generate a report for the extrapolation. And we're going to show the illustration of that soon. But the main idea is that this is a priori a Jupyter notebook where you have, let's say, several standardized visualizations of what's going to be the redemption price over the next week, the redemption rate over the next week, will happen if you adopt, for example, a behavioral model where users don't do anything, or where users reproduce the past behavior. So yeah, we're going to spend some time going through that. And after we have all those results, ideally, all of this would be stored on some output locations. So on that workflow, we could use a variety of, let's say, of places. We could use, for example, data lakes, EPFS, and GitHub. For now, we are only storing locally, but it's relatively straightforward, for example, for writing something for storing on data lake, and it's really, let's say, operator choice. And that's it for the workflow. So just for enumerate, when we were designing the digital twin, we had 4, let's say, key properties that we had prioritized. First one, which is modularity. So it must be easy, for example, for you to test, for example, what happens if you change a user action model, a behavioral model, if you change the parameters. It must be easy to automate in the sense that by passing just one simple command, you can run the entire workflow so that it's easy to implement a cron job or implement scripts that, let's say, automate the whole process. Third one is that it must be easy to consume. So if you run the digital twin, it must be easy to see the results. And fourth, of course, it must be coherent with the real system, which is established through backtesting. And that's it for, let's say, for the essentials of what is the digital twin. Before going on to environment preparation, do you guys have any questions about it? Or, I mean, maybe more clarity on some aspect?
I think we're good. I think you should continue for the recording's sake, just working through.
Okay. So given that now we know what is the digital twin, the first step in order for you to be able to use and consume the digital twin output is to prepare the environment. So in order to do that, you need 2 things on your environment. First one is that the digital twin runs on Python 3.9. This is a hard requirement. Python 3.8 will not work. So you must use Python 3.9 or more. Second one is that there is a file called requirements.txt that contains all the Python libraries that is required for running the digital twin. And you must install it through pip. By achieving those 2 things, you have a machine that is able to run the digital twin. So this is what is required for the environment. And of course, you must also clone the digital twin repo on a local machine or a remote machine. And that's it for the environment. About the input and output, and here we are talking really about input and output on a user sense. The digital twin have 3 places where you can, let's say, have an input, and 2 places where there is an output. Those 3 places about input is first that the digital twin does have a command line interface. We're going to see soon how it works. But by passing a simple terminal command, you can, for example, run the entire digital twin. You can configure certain options of that. It's extensible. So if for example, you have additional needs or you need additional customizability, it's always possible to implement additional features to the command line interface. The second place where we have input is at the execution logic.py, which is, let's say, the most user-facing code file that we have. And it encapsulates the entire execution flow from prepared data through extrapolation. So there is possible, for example, to put, for example, what happens if you have a parameter changer of the controller in the past, on the future, or what happens if you want to, for example, to test additional behavioral model. So that place is the second network place where someone would want to put input. The third one is the templates folder on the digital twin folder, because the reports that are being generated on the digital twin, they are Jupyter notebooks, they are functional Jupyter notebooks, and the digital twin uses those notebooks as being templates, so that every time that the digital twin is executed, and report is generated based on that notebook. And as for the output, the first place where we have our output is on the data runs folder. We are generating several CSV files. They are compressed on gzip, so it's important to have it's important that the environment supports gzip if you want to manually consume those files. Those files can be integrated into traditional data science workflows. So if you want to do a separate analysis, or you want to get more detail about, let's say, of what's happening inside the simulations, there is full transparency in there. And the second output is the HTML files at the reports folder, which is essentially the rendered version of the notebook templates. The notebook templates are using Plotly, so those HTML files, they are interactive. And as we are going to see, this is really powerful for getting insights about the inner workings of the system. So, okay, now let's go to the folder structure of the digital twin so that we have a grasp of, let's say, of how it's structured. So here we have a Jupyter notebook that is right now is at the hot folder of the RAI Digital Twin repository on GitHub. And we have all those files and folders. As we can see here, we have this data folder. The data folder contains the runs folder, which contains all the output from the digital twin. And as you can see, there are some things here. So first one is that every generated file starts with a date. The idea here is that every time that you run the digital twin, you are generating files in a way that, let's say, you can always keep track of the past. This is important because first is a way of, let's say, establishing provenance. Second one allows you, let's say, to sort of having a data log of what's happened. So this is interesting because, for example, you can take, for example, past predictions and compare against the actual reality. So you could take, for example, an execution that happened 3 weeks ago and see how it compares with the execution today. So this is a really powerful thing for validating. And as we can see, there are several names after the data, like, for example, retrieval, backtesting, extrapolation, historical, and meta. This is really for bookkeeping, which process of the digital twin has generated those files. So for example, the retrieval file is really about the RAM data that we have collected from the graph and HRTL. So it's just downloaded data. Historical one is the retrieval one, but cleaned and processed so that we can, let's say, use inside the digital twin. Backtesting is the digital twin digital twin execution of the, let's say, of the run on the past. So we are using the historical data set as an input for the cadCAD model, but we want to see how certain variables of the digital twin behaves on the past. So this is really about, let's say, the digital twin interpretation of how the past should have went if the cadCAD model is true. There is also the extrapolation file, which is really about having a time series over the future. So all the data contained on the extrapolation file is only relates to the future. And we also have the meta, where we put, for example, some metadata, some parameter values, timestamps, anything that, let's say, for some reason we think that should be important and should be kept at runtime. Going back to the root folder, we have also those other notebooks folders here, like, for example, notebooks. This is really about having Jupyter notebooks for separate analysis. They are not related to the digital twin itself, but they could be useful, for example, for storing if you want to do, for example, a separate analysis over the results. We have the RAI Digital Twin folder, which is really about the cadCAD model. We're going to go into detail soon. And we have the reports folder, which contains all the HTML reports. And on the RAI Digital Twin folder, we have the templates folder, which contains any notebooks that we want to render at runtime. So they are going to be reports. We have a folder containing, for example, the models of the digital twin. So there is an entire cadCAD model inside here, and we're going to see more detail on the walkthrough, the specific walkthrough. Notice that, let's say, it's possible to have several versions of the digital twin model. So depending on the mechanisms changes, depending on the iterations of the controller and so on, it's possible to have multiple versions. Like, for example, if the EMM changes from Uniswap to balancer and so on. A third folder inside the RAI Digital Twin is the test folders. So the idea here is that the digital twin has been designed in a way that makes extensive use of unit tests and integration tests in order to make sure that all mechanisms are trustworthy and that, let's say, they are not going to break into a variety of circumstances. It's really about, let's say, validate the code before operationalizing. And we are going to see how to execute things soon. And yeah, that's it for the folder structure. Any questions about the structure and so on, or should I proceed?
I think you should proceed.
Okay, so now I'm going to show how to use the digital twin inputs and also how to consume some of the outputs. The most natural place of interacting with the digital twin in terms of input is really by using the command line interface. And it's simple as you could get. You simply pass Python-m RAI Digital Twin on the command line interface. In order to see how it works, you would open, for example, a terminal here. And then you would pass Python-m RAI Digital Twin. By doing that, you are doing the entire execution flow of the digital twin. And this can take a while because, it consumes a lot of data. So while it is runs, I'm going to cheat and open a terminal here that I've already run this morning. So by passing that, we can see that we go through several steps. So first we retrieve the data, as we can see here. We retrieve, for example, the early stats, the system states, and also the history of the saves on Reflexer. This can take a while. Most of this data come from the graph. After that data is retrieved, we prepare that data. So we do some post-processing to make sure that the data is in the best format possible for executing inside the cadCAD model. And then we go to backtesting, which is essentially injecting the past data inside the cadCAD model and making sure that, let's say, the loss is good enough. So for example, here we have done an execution of the past. And notice that we have here a metric called backtesting loss, which is 0.3%. So we're going to see the inner workings of that in detail on the walkthrough. But the main point is that this is a measure of how much the cadCAD model is performing against the historical data. And our loss function that we are using is the absolute error. So our absolute error is 0.3%, which is a good sign. It means that, let's say, if you take the mean values of the validation metrics, the model is 0.3%, has a 0.3% residual in regards to the true historical values. We have the entire step here for fitting stochastic process. This is really about, let's say, fitting the Ethereum versus USD price. We generate several, we take the past historical data from them and we fit statistical distribution for them. On the extrapolating exogenous signals, we generate future price data, and we can generate several of them. In that case, we are generating 10 time series of prices. but this is customizable on the execution cycle or the command line interface. So for example, if you want, for example, to test more scenarios, you could do, for example, 50 as extrapolations of the price feed and so on. The last step is, which is really, let's say, the shared part, is about extrapolating future data. So here we are using of all the behavioral models that we have configured inside the cadCAD module together with several parameters. And we are essentially generating data into the future and generating a data set about that. And once this is done, we export those results. So this is really about, let's say, taking the notebook template and generating an interactive HTML file so that we can consume easily that data. And after that, we are done. As you can see, the execution here took 3 minutes on my local computer. It can take more or less, depending on the simulation configurations, on the machine. So for example, if you want to increase the amount of price data or increase, for example, how much days of extrapolation you want, the time will increase. But if you want less, then the time will decrease. So it's really customizable in the sense that, I mean, that's how you interact with through the command line interface. There is also the notebook templates, which is another natural place to interact with the digital twin, because here at step 6, we are simply getting that template and, let's say, execute it again. And in order to see how it works, let's open the template. So RAI Digital Twin, templates, extrapolation. So this is a conventional Jupyter notebook, as you can see here. The idea here is that by using Jupyter tags, if you click, for example, at the gears, the idea is that if you click, for example, at the base path here before the load data, it has a parameters tag. This means that every time that the digital twin is executed, this variable is going to be replaced so that it makes use of the latest data. By doing that, we are able to customize that notebook so that every time that we run the digital twin, all of those cells are run again. So just to see how that templating works, we just pass that base path. We load the data here and also here. There is a lot of pre-processing going on here, but this is really a data science workflow. So I will skip a bit the details. But the main point is that you could do, for example, conventional data science visualizations by using Plotly, plotting all kinds of variables. So for example, here we have, for instance, visualizations for the prices over several scenarios, and so on. Okay, so now that you know how our template works, we can see the output of those visualizations when we generate that. So for example, if you go here to reports, we could select, for example, one of the executions, like for example, this one, and we could open a browser tab. So this is an interactive HTML file. It's an independent file, so you could share, for example, through Slack or could share on GitHub. You can simply copy and send to whatever you want to share. And the template is really made in a way that, let's say, contains all the visualizations that matter for, let's say, a given audit. So for example, this is one template that we have created that, let's say, summarizes the main metrics and outputs of the digital twin. But depending on the needs of the operator, if you, for example, there is the need of having a more detailed analysis about some aspect, maybe computing the phase space of the user action versus the price, it's really about, let's say, adding a new cell to the template and running again. So on this template that we are using now, we have, for example, here a visualization of prices over time that contains, for instance, the past data here on head, and the data after the date of the execution, which is the feature here, and as you can see by extrapolation. So we have several colors. So for example, lines that are blue or head, they are past data. So Red ones, they were generated by the cadCAD model, and blue ones, they are data that was injected inside the cadCAD model. So the price is one, it doesn't, given that the cadCAD model doesn't backtest the price data, the two are the same. But the main interesting bit is really about the extrapolation. So you can see here, for example, that we have different scenarios of price. So for example, the Ethereum price, the prices are equal for all extrapolation scenarios because the extrapolation, they are behavioral mechanisms on the high systems. So they don't change the Ethereum price in regards to ASD. But you can see another history here on the high market price. So for example, if you look, for example, at the extrapolation, the green extrapolation here, you are going to see that the price of the high market pricing in dollars is going to be different if you compare, for example, to the cyan one, as you can see here. The reason being is that behavioral models, they can't change the market price depending on how you set up them. And I think about those interactive visualizations, there are some useful tricks that helps a lot with insights, and it's worth mentioning that, for example, you could do a double click on the lines so that you see just one scenario, or a double and click again to get out the others, or you could do just a single click so that you hide someone. And we are going to use that for, let's say, having a bit more clear view. Besides the price, we also have here visualizations for other things, like, for example, the controller state, which is really about the redemption price, the redemption rate, and so on. So, for example, on the first visualization here, we can see the evolution of the redemption price per time. Blue one is the actual redemption price. Red one is the redemption price according to the to backtesting, which is, let's say, the model interpretation of how things should have went. Notice that there are some deviation, and one of the results here is that one of the reasons of why it is happening is that the controller state depends also on the error term, on the proportional term. And we don't have information for that. So when we execute the backtesting simulation, we need to set that redemption price error to 0. So there is definitely a room for improvement there if we have access to that proportional error measure. But anyway, look at the extrapolation. It works by doing the following. We get the last historical point, and then we run the cadCAD model on the extrapolation mode so that it makes use of behavioral models and so on. So you can see that depending on the extrapolation scenario here, we can have several sets of results. The scenarios are indicated by the parentheses. So we have two behavioral models that we are using right now, the EMM and the CSI. We are going to enter in more details how they work soon. But just for, let's say, illustrating, if we take, for example, the cyan one, which is EMM equals 1, CSI equals 25%, we can have this scenario of redemption price where the price remains sort of stable. But if we take, for example, this one, where there is no behavioral model at all, you have, let's say, all these variance. And of course, you could see, for example, what happens when, for example, you have just one behavioral model until it is deactivated, like this one, or when you switch terms, for example. So this is a key feature of the digital twin because it allows you to explore easily, let's say, the implementation of behavioral models in a way that you can compare against each other. So going back here, we have, for example, the redemption rate in terms of percentage per hours, and also percentage per years. And other things like, for example, the proportional error that the cadCAD model has generated and the integral error. Notice that the integral error is 0 because the integral term is deactivated. So it is always going to be 0 unless it gets activated at some point in time, as expected. Another thing that we can get is the visualization for the token state, which is really about, let's say, visualizing how much depth we have, how much Ethereum locked as collateral we have, and also how's the situation of the Ethereum and high on Uniswap. So we can see here that, let's say, depending also, we have the historical data here in head. And also, depending on the behavioral model, we can have different outcomes for the future. So if we pick, for example, the high depth and the Ethereum collateral, we deactivate, for example, the ELMEM, we are going to see that they are constant, because that's the way that the CSI behavioral model works. The CSI model supposes only movements at its map. It doesn't suppose movements at the surface itself. But if we take, for example, the EMM model, which are those two here, you have a different history, because this model, it does consider the possibility that the users, they are going to do movements on the high safes. And yeah, so those are some of the things. That's how the interactive visualization works. The specific details of those behavioral models, we are going to walk through them soon. Okay. So now that we know how to, let's say, to execute the digital twin, and also we know how to consume the output of the digital twin, the next natural step would be to start, let's say, understanding and modifying the existing code base. But before you jumping straight into the code, it's worth to, let's say, take a minute to understand how unit testing on the digital twin works, because this is a good starting point for understanding the code, and also to write additional unit tests so that you make sure that the digital twin, let's say, keeps being consistent as things get modified. So the way that unit testing works is very simple. You simply go to the folder of the digital twin, and you pass python-m pytest. PyTest is a testing framework, is a Python testing framework, maybe the most feature-rich one that there is out there. And when you do that, it's going to execute all the available tests. So as we can see here, we have a variety of tests. So we have, for example, testing regarding the PID controller on reflexer. We have also here a test about governance events, because the digital twin does make use of governance events to keep track of parameter changes on the past and also on the future if needed. We also have here, for example, tests for testing the backtesting logic, for the getting the data retrieval, testing the model execution, testing the certification. So it's really a comprehensive coverage. And one natural way to understand how the code works and so on is really by going through those tests and see how they work. So for example, if we go here at RAI Digital Twin and we go to the test folder, and we want to know how the model is executed, we could go to model run. And this is how the model is executed. We have, for example, his run call here that, let's say, gets the digital twin initial state and parameters. And if the length of the results is equal to, let's say, a certain amount, then the model is executing. Of course, this is no assertion, this is not sure that the model is valid. This is just make sure that the model is running. In order to make sure that, let's say, the model is valid, we would need to have other tests. Like, for example, if you go to the models and the parts here and tests, we could have, for example, tests for the controller itself. So, for example, we have a pretty robust coverage about, let's say, making sure that the redemption rate is working as expected. We have also several scenarios here for making sure that the redemption price updates is happening as expected. And also some tests, for example, for what happens when you change the controller parameters on the fly. And let's say a good practice is that every time that you modify the digital twin code or you add a new mechanism, make sure to always run the test framework to make sure that things are still working. And if you do add any feature, use the opportunity for, let's say, adding a new unit test to, let's say, validate that before, let's say, doing the whole execution that can take lots of minutes. Because a test executes in 2 seconds, but the execution can take a lot longer. And given that, I think that we can have our first dive into the code. And the natural place to start is on the code base regarding the extrapolation cycle, which is the logic where, let's say, the entire workflow of the digital twin occurs. So the execution logic is contained on the RAI Digital Twin folder, and it's a file here called execution logic. This is the main file that gets, let's say, executed when you pass the command line interface. And there are several things, so we are going to go through it slowly. But the place where where the action happens is here, the extrapolation cycle method. We can notice that it does have several arguments, like, for example, the place where the data is being generated and downloaded. We could also, for example, have some option on how comprehensive is the backtesting. If you are going to backtest it 14 days or 21 days or maybe 2 months, it's an argument in there. Right now it's 2 weeks, but this could be tweaked. This could be an argument for the command line interface. We have an argument of how much price samples to generate. So we are generating 10, but it could be more. It's really, let's say, a choice of the operator. And also we have arguments here for the extrapolation. So for example, here, we are generating 7 days of data into the future, but this could be more, or it could be less. And we also have the option of generating multiple samples of extrapolation, so that, let's say, instead of for each parameters with having 1 sample, we could have 3 samples, 5 samples, 10 samples. It's really at the criteria. Just notice that, let's say, there is always a performance trade-off. So for example, if you get too aggressive with the samples, the execution time is going to go up. So sometimes you need to make a decision, for example, between having a comprehensive parameter sweep or doing more extrapolation samples. It's right. It's really, let's say, experimental choice. And let's say you need to make sure that, let's say, the execution interval of the digital twin is consistent with that. So for example, if you want to run the digital twin hourly, it can be very complicated if you want to do, let's say, a large parameter sweep and generate lots of samples at the same time. But if you run weekly, then you have more leeway into that. So this is an important observation to make. There is also 2 other options here. That this one about useless data is very useful for debugging, because it's possible to run the digital twin in a way that it doesn't download the last data. It only gets the last data that has been downloaded, and let's say it runs the cycle on that. This is very useful for debugging, because sometimes you are adjusting, let's say, testing new features, and you don't want to download the full thing. And also you could skip, for example, generating reports. The extrapolation cycle really does, let's say, all the things that we have some on the command line interface. So for example, on the retrieving data section, the 0.retrieving data, as we saw on the terminal, it's really about, let's say, preparing the folder and also downloading the data depending on the useless data. And the data is actually retrieved, let me see here, retrieve data. So everything regarding data retrieval is contained here. Specifically, this retrieve data function that, if you want to see, we have a function here at the top called retrieve data that contains a download data depending on data range and exports that to a CSV. And this comes from the retrieve data file here. And this is sort of the pattern for the other sections too. So for example, if we get the preparing data, we are using that prepare function here that, let's say, gets the historical path for the data and also the path for governance events. And we have 2 variables here called backtesting data and governance events that are going to be used on the next steps. On the backtesting module, probably this is our first, this is where action actually happens by using cadCAD module. We have, let's say, this first line here where we pass the backtest data and governance events. By doing that, we are essentially doing a cadCAD run. And with that, we have results. And we export those results to CSV files. And also, let's say we start out the timestamps just for keeping track of the time, and we generate metadata about that. And this is exported, and that's it. As you can see, the extrapolation logic function is really, let's say, a wrapper to making sure that, let's say, we glue the data together and that we handle, for example, the exportation of data and so on. We have here, for example, the step here for fitting stochastic process. As again, it is the same pattern. We have a function here for stochastic fit where we have a dependency on the backtesting data. And by doing that, we have the stochastic parameters, which is a dictionary. After that, we go to extrapolation. So we have another function here called extrapolate signals that take those parameters, take the amount of data that we want to generate, the initial price, and the number of samples. And of course, all those variables here come from here. So for example, the NT, the extrapolation time steps, is an argument of the extrapolation cycle method. Price and samples, same thing. The initial price, they come from the historical data. So we are getting the last data point of the historical data set, and we are using that as a starting point for extrapolating those signals. And we have also here the step for extrapolate future data. So here we are using the cadCAD model for projecting into the future. So same pattern. We have the extrapolate function here. It takes the signals that we have generated as an argument. It also takes, let's say, the results from the backtesting, so that it uses that as a starting point. It takes also, let's say, any governance events, which is controller parameter changes, essentially, and also arguments of how much data points we want to simulate. And after this is done, and this is essentially a pandas data frame, we export that to a CSV. And also we have all those things. We can go, for example, to the templates folder here, and then execute a notebook by modifying that variable that I showed to you on the gear symbol. And after that, it's done. We have gone through the entire extrapolation cycle. So this extrapolation cycle is really, let's say, a function wrapper. It's really, let's say, a way of, let's say, gluing together all the things and make sure that we can export the data. Also, we have, let's say, a clear sight on how each thing is interact with each other. And by looking at the specific functions, like, for example, the extrapolate data, we could get more insights on how the model is, how we are doing, for example, to simulate that. So, for example, the extrapolate data here, we are setting up the cadCAD model so that it's ready to do projections on the future. There are several steps here, so maybe it makes more sense to go backwards rather than from the beginning. The idea is that there is a data frame that I generate through the EasyHam. EasyHam requires an initial state, requires the parameters, requires the partial state update block, and also number of time steps and number of samples. And that's really all that we need to run the module. The tricky part is really to setting up the initial state and the parameters. So we have a lot of code here that is really about just for making sure that the initial state and the parameters are set up correctly. So for example, those are the parameters that extrapolation is using. For example, we are not performing backtesting. We are not overriding the times because, I mean, RAI is a hybrid system. So what happens is that on backtesting, we can have, let's say, variable interval between the data points, and on extrapolation, they are fixed intervals. We set up the backtesting data parameter as none because we are not backtesting anything. We are setting up here governance events also as none because for this purpose, I'm not supposing that we are going to change the controller parameters of the future, but it's possible to tweak. We could set up, for example, sweeps. So for example, there is a parameter here called use ML model that allows, for example, to sweep if we want to activate it or not. So we are testing both cases. And we could also sweep, for example, the convergence swap intensity para behavioral model. So every behavioral model that you add to the digital twin, you could do sweeps here. It's really about, let's say, adding a new parameter to the cadCAD model and updating it. Okay, so now I'll continue to the primitives. The idea is that in order to make the software engineering of the digital twin a bit easier and also to make, let's say, the data flow between the digital twin more consistent, the RAI Digital Twin software architecture makes use of several classes and types in order to keep that more consistent. And having understand of what they mean and also what are the definitions can help a lot when you set up new behavioral mechanisms or also to set up new simulations. So all the primitives on the digital twin is contained on the typos.py file. I'm going to go over here soon, but we have here several Python objects that we use for, let's say, for making the code more legible. Like, for example, we have definitions of all the measurement units that is being used inside the digital twin, like seconds, days, height, which is essentially the each own height. Also units for currencies, and so on. This is used a lot because the digital twin makes extensive use of typing hinting to indicate, for example, what we expect for each function or process or anything like that. So, for example, if we take an object like, for example, the parameters of the controller, we have the key P, key I, leak factor, and period properties. And all of them, they have a unit, like, for example, per USD or per USD seconds or percentage. So keeping track of those measurement units have a double function of first, indicating what is the concrete computational object, if it's a floating number or an integer. But there is also the function of keeping track of, let's say, what's the measurement? It's Ethereum, it's high. So this helps a lot, let's say, making sure that everything is consistent when doing operations. And about the primitives or classes that we have some types here that may be worth going over. So, for example, we have types here for the governance events. This is really about, let's say, encapsulating something that allows us, for example, to change the high controller parameters on the future, on the past, because the controller parameters, they are not static. They can change depending on voting or proposals and so on. So those two objects capture, let's say, how should be structured one of those events. But for the cadCAD model itself, the most used ones are those ones here. So for example, we have here, for example, object for the controller params, which encapsulates, let's say, the PID parameters, like, for example, the key p-value, the key value, leak factor, period, and also if it's enabled, because the model must be able to represent, for example, what happens if the controller is disabled. And if there is any update, for example, to the controller, to the PID controller, it's possible to add new properties here so that the model is aware of that. The main point of having those classes is really to, let's say, to have, let's say, something that encapsulates the properties of those common objects. We have here also object for the controller state, and we are using here 4 properties: redemption price, redemption rate, proportional error, and integral error. So this is object that we are going to use a lot on our model. We have the user action params. So this is really about the behavioral model, because we can have a variety of just for this ambiguity, the idea of having a behavioral model is exactly to, let's say, to have a model of what are the actions that a user is going to take. So you could think of that also as being behavioral params. But anyway, we are using, for example, right now, one model, which is the EOMM, that makes use of all those 5 here in order to, let's say, to model the past behavior. So depending if, for example, if you have more complex behavioral models or if you need additional params, that would be a natural place to consider. But right now, our model considers that, let's say, the user will care about the liquidation rate, the debt ceiling, the swap fee, and also if it considers the liquidation rate at all, and the intensity. Intensity is really about, let's say, how aggressive is the behavioral model. Another object that we have here is the token state. The token state consists essentially of, let's say, the status of the high token. So given our past research, let's say one insight that we had is that we could characterize a lot of the token dynamics by having those 4 properties, which is total height that, let's say, was minted through depth, how much Ethereum is locked at the safes as collateral, and also the amount of high and Ethereum on reserve on a Uniswap liquidity pool. We also have here some method overrides so that we can, let's say, do subtraction, addition, and multiplication operations over this object, because this comes in handy when doing the model. There is also object here about transformed token state, because another way of, let's say, interpreting those, this state is that if you take into consideration the fact that you have a depth ceiling or the liquidation ratio, there is an alternative choice of coordinates that it can be very powerful in order when compared to get some behavioral models. I want to go into the specifics of this now, but it's worth knowing that, let's say, this is used by one of the behavioral models. Other primitives that we have here is, for example, a primitive for the backtesting data. So we have, for example, this encapsulates essentially data on the path. So we have 4 properties here. All of them are dictionaries, and all of them are keys. So this is essentially a key value mapping over the path. So we have, let's say, things that indicate what should be the token state and let's say the heights and the controller state on the past. This is used by the backtesting part of the digital twin, because given that the backtesting does not test the behavioral models, but only the, let's say, the controller itself, we want to know what the controller is going to predict of the controller state, given that, let's say, you know the other things. So this encapsulates the dependencies of the backtesting part of the model. And also we have other classes here, like, for example, a class about, let's say, the optimal action, which is associated with one of the behavioral models, the action state, params. They are all used for internals on the code. And also some helper functions here, like, for example, coordinate transformations and reverse transformations. But this is really getting at the inner works of the digital twin. Okay, so now that we have a grasp of the input and output of the model, the extrapolation cycle itself, and the primitives, we are now prepared to do a more detailed walkthrough through the model, through the cadCAD model. So this is going to be a more dense part. So as I said, in terms of the cadCAD model, the interaction with the extrapolation logic occurs, for example, on the backtesting and the extrapolation. This happens here at the easy run, where we pass the initial state, the params, and the partial state update block. So in order to understand the cadCAD model, we need to understand those 3 here. So let's do a dive into them. First one is that the digital twin V1 model, if you go to the init file, you have some things here that indicate some locations. So for example, the parameters are located on the model.params. The initial state is located on the model state variables, the default initial state. It's important to note that on the extrapolation cycle, both the parameters and the state variables, they are going to be overriding. So those are the default, but just because it's default doesn't mean that they are going to be actually executed. But let's say for teaching purposes, we have that. And the third one, we have here the partial state update blocks. So those 3 are what we need to understand in order to make sure that we understand the model. So let's start with the initial state. So let's go here to model, state variables. So the variables that we have on the model are those 1 here. So we have a states that, let's say, represents essentially the time evolution. States that represent exogenous states, so things that are outside the control of the system, which is Ethereum price, the market price of high, and the spot price. We have also here the controller state. So here we are talking about two things. We are talking about the parameters of the controller, which is the KP, the KI, the leak factor, and the state itself, which is the redemption price, the redemption rate, and so on. And also the proportional error, for example. And the last one is the token state, which is how much high in depth or how much locked Ethereum. Notice that both the controller states here and the token state, they are making use of the primitives that we have laid out. So the pit params variable here, state variable, makes use of the controller params primitive. The pit state variable makes use of the controller state class, and the token state of the token state class. So it's important to note that. And of course, we have here, so for example, some candidate initial values. Those are kind of arbitrary because on the digital twin execution, they are going to be overriding. So those values that are here is really for, let's say, debugging purposes. About the parameters that the digital twin uses, we have them here. So we have parameters that, let's say, are related to the system itself, like, for example, the governance events. Governance events is really about does the controller parameters change over time or not? If they change, when do they change? And by how much do they change? And it's interesting because the governance events, they can be used for two things. First one is they can be used for making sure that the cadCAD model is consistent with the actual parameters. But the second one is that the governance events can also be used for experimental design. Because you can, for example, create governance events into the future, or maybe even create fake past events so that, let's say, you know how things would have been. So governance event, tweaking the governance events is, let's say, it's a really, let's say, a quick route in order to do shock analysis, to do counterfactual analysis. So it's important to, let's say, take note of that. There is the PI bound parameters. This is really a specific thing because the way that this market, the controller, the PID controller works on the smart contract, it does makes use of some bounds. So we put that in order to make sure that, let's say, the cadCAD model is consistent with the real controller. But this is really, let's say, a very fine detail. We have here a parameter for the exogenous data. So this is really about injecting data inside the cadCAD model. So most of the time, this is going to be price feeds. So here we inject price feeds. Notice that also we have, let's say, parameters that are specific to backtesting, like those one, and parameters that are specific to the extrapolation. So when you are backtesting, the model that you are executing is not quite the same of the extrapolation. There are some differences. When you are executing backtesting, you are not doing, for example, you are not using the behavioral models at all. While when you are doing the extrapolation, you are not, for example, injecting data like you are doing on backtesting. So this is a thing to note. For backtesting specific params, the first thing is that we have a hits param, because when you are backtesting, you don't have a definite time interval between data points, because the block height of Ethereum is stochastic. It has an average, which is sort of 13 seconds, but it's not quite that. What this means in practice is that when you are performing backtesting, you must also keep track of the exact time where things has happened. So this heights param captures, let's say, the exact time where things has happened. So it's really, let's say, to make sure that the model is consistent on the past. The backtesting data param is really about injecting data inside the module. So we are injecting essentially the token. We are essentially injecting here the token state variable. On the extrapolation specific params, we have a lot of other params. So for example, on the user module, we have a parameter here that controls if your simulation is going to use that model or not. this is an interesting pattern because, for example, if you think about a third behavioral model or a new behavioral model, a simple way that, let's say, you could do to make sure that, let's say, you can test and compare and A/B test against other behavioral models is to add a new parameter here and, let's say, use true or false to control if you want to execute it or not. We also have, for example, the conversion swap intensity, which is related to another behavioral model that, let's say, takes a number between 0 and 1. We are setting here as none, but yeah, this is going to be overriding anyway on this extrapolation cycle. By setting that between 0 and 1 and by doing sweeps on that, we can test several scenarios for that behavioral model. And also we have here parameters for the other, for the YAML model, like for example, the YAML alpha and the verlag. So this could be a single parameter, this could be a parameter sweep, but all of this is tweakable at the extrapolation cycle. And also we have other specific parameters to the extrapolation, like for example, the extrapolation time delta. So the idea here is that on the extrapolation, we are doing, let's say, simulations every certain amount of time. So they are fixed time windows. And in this case, we are doing one data point per hour. So on the extrapolation time delta, we control that. On the user action params, we control specific things regarding the user specific things in regards to the user behavior. And same thing here for the backtesting action states. And of course, we have a last parameter here, which is perform backtest, which can be true or false. And going now to the partial state update block, which is where the actual model logic happens, we have all those blocks here. Notice that some of them, they have, for example, a comment here called only used on backtesting. This means that if the model is not on backtesting model, they are going to be ignored. So to go over the partial state blocks, first we start with a block doing time tracking. So if we are backtesting, we are going to get the heights param and resolve the time passed. If not, we are going to use the extrapolation time delta. So we know exactly how much seconds has passed each time step and what's the time delta. So that's for start. Second part is about governance and backtesting. So here we have three things happening. One is about governance events, which can change the PID params here. We also have here the P backtesting, which will change the token state. And also we have the exogenous data here, which will change the Ethereum price. Oh, by the way, backtesting data also updates the market price. So this is really about, let's say, changing the controller parameters and also inject the data for token state, Ethereum price, and market price. And we can go over on the code soon. After we have injected that data, the third step is to compute the controller error. So we observe the errors. I mean, we get the market price and we get the spot price. And we compute the error of them. And we update the PID state. So we compute the proportional error and the integral error. And then we have a block here for computing the redemption price and rate. So it's pretty simple. It's just a PID. It is just consists essentially of update the pitch state so that we apply the redemption price and rate formulas. And after we have, let's say, observed what is the expected controller behavior, we have this block here, which only executes on the extrapolation step of the digital twin execution. So we have this policy here called P user action that controls what is the behavioral model that we are going to use. And based on that, we control the token state. So we are controlling if the user is adding or removing liquidity on Uniswap, if he is swapping on Uniswap, if he is adding or removing debt from the safes, and so on. So that's how, let's say, the logic of the models is structured. And we could go into a bit more details. So for example, if we go on the P user action here, because most of the time, this is, let's say, where the cool part of the digital twin happens, because this is where the behavioral models is contained. So the P user action is contained inside the parts token state, as we can see here. So let's open that file here. And that's the P user action policy here. Let's do a walkthrough to understand how it works. First thing that it does is to check if it's performing backtesting or not. If it's false, then we have several things that we're going to do. Else, we are not going to do anything. Assuming that we are on the extrapolation phase, so we have then this second conditional here. And also this other conditional. So let's take a time to understand what happens. On the first one, if we use the EMM model, we have some actions here, like, for example, preparing the action state history and the fit prediction action. And depending on the output, we simply do nothing. Else we have an action here that is going to be added to the new state. That new state is really, let's say, the effect of the behavioral model on the token state. Notice that it has both an action and that ARB action. And there is also another thing here that is the second behavioral model that we have, which is associated with the convergence swap intensity. So if it's not known, we are going to do several things here. Else, if it's not known, these are actually simply 0 for everyone. So if the user model is false, the action here is going to be 0, 0, 0, 0 on the token state primitive. Same thing for the RB action if the intensity is known. And the sum of RB action is going to be 0, 0, 0, 0 on the token state. So we are not changing the token state. But if the intensity is not known, or the model is true, then the action is going to be another thing. So just to explain a bit how it works, it's not exactly the job of the walkthrough to, let's say, enter into details of how the behavioral model works, but it's important to understand how you could add a behavioral model or how you could modify them. And by the way, if you want to add a behavioral model, you could do something like, for example, plus new action. And you could do, for example, a conditional, like, for example, if params use new behavioral model is true, then the new action should be, for example, something like token state EBCD. And your behavioral model must be able to compute those 4 letters. So EBCD should come from, let's say, new behavioral model function. Else, new action equals token state 0, 0, 0, 0. So if you want to add a new behavioral model and you want to sweep that, that's what we will do. But anyway, just to go, let's say, to do a quick dive on the existing behavioral models to get a grasp, the convergence swap intensity, it's really about having an arbitrager of the system that, let's say, keeps trying to make the high market price at Uniswap converge to the spot price that's being used by the controller. So it does a bit of operations here. There is a HackMD document that is on the README that explains the exact operation of that. But the main point is that we are not, for example, changing the last 2 terms here on the token state, because the first 2 terms are about the reserves on Uniswap, and the last 2 here are about the ethereal collateral on the high debt. Depending, for example, on the, let's say, on the optimal high swap, and depending also on a handle value multiplied by intensity, we are going to have that RB action here. More details about how this works, how this exact swap was derived, is contained on a HackMD document that has a link on the README. The user model has the same history. It's a behavioral model that makes use of exponentially weighted moving average over the user action that has some coordinate transformations together with a var model. It's a bit too much convoluted to explain it right now, but if you go to the fit prediction action, it contains all the core logic of how that happens. So this is located at the RAI Digital Twin .system identification file as the fit prediction action. So it would be contained here at RAI Digital Twin, system identification. And if you go here below, you have this fit prediction action that contains several steps, like, for example, retrieving errors on the transformed coordinates, doing power transformations, training the var model. And I mean, it's really out of the scope of this walkthrough to, let's say, to go onto the specifics of how this works. Anyway, going back to the partial state update block, we now understand how the behavioral model works. So it may be worth now to, let's say, to see how the redemption price and rate is calculated and how the controller is observing the errors. So for computing the redemption price and rate, we have simply the SP redemption here. And let's go here to the parts. And it's located at, let me see where. It's located at the parts controllers file. So parts controllers. And then we have here this file called SP redemption. So the idea here is that we depend on all those variables here. So it depends on the controller state, or depends on the controller params, and also the time delta. And this is where things happen. So for example, interest is computed by getting the redemption rate and powering by time delta, because the redemption rate as it is here depends on the, it's a second rate. We update the redemption price by multiplying the current redemption price by that compounded interest. And we have functions here, for example, for compute the redemption rate, given the parameters and the state and the PI bound params. And also we have logic here for compute the hourly redemption rate so that we can compare. And we create this object here called the controller state that contains the new redemption price, the current redemption rate, and also the state of the errors. And we could go into, we could even go through the redemption rate function here, but the main point is that this function, it encapsulates essentially the smart contract logic of the PID controller. So it's really about getting KP and multiplying by the proportional error, using logic for TKI. There is also some logic here for the bounds. So this is sort of a this is a high fidelity representation of the smart contract. So I will not go into details about that. And going back here to the partial state update blocks. So yeah, here essentially we do that. There is also the part about observing errors. So if we go back here on the controllers, we can have, for example, the policy of P observe errors, and it is as simple that it could get. We simply get the redemption price and subtract by the market price, and this is the observed error. And by doing that, we can, for example, store the errors. So we compute here, for example, the proportion on the integral error. Like, for example, the proportional error is this one here. So new error is simply the difference here. And the integral error is a bit more complicated in the sense that, let's say, you need to do the numerical integration by the trapezoid rules so that you take the mean error and multiply by the time delta. But it's a bit out of the scope, let's say, explain the exact specifics of how the integration works. And about, let's say, the author here, probably this is the most convoluted block here, governance and backtesting. I'm going to walk through, let's say, how those three policy here works, because especially the governance events can be very interesting for example, testing effects of parameter changes and shock analysis. So if we open here governance.py, we have this P governance events policy here that get the governance events dictionary, that is a param. And the idea here is that the governance events key is always a time step. So if the current time step is contained inside that dictionary, then we have an event. else, nothing is going to happen. And there is a function here called decode event that, let's say, parses what has happened. So the idea here is that if you pass the event to it, depending on the kind, there are some actions that could be took. Like, for example, if the governance event kind of that event is, for example, the PID parameter has changed, then the action is to do the following. You get the action dictionary, you set the key as PID params, and you set as being equal to the descriptor.